Hello everyone, welcome to this video. In this video, we'll be looking at a property that center of any group that is a subgroup, right? Let's see how. So the property here tells us that the center ZG of a group G that is a subgroup of the group G, right? So let's try and prove this thing over here. So for the proof, let's see, for the proof we shall use two-step subgroup test in order to prove the result, right? And what is this two-step subgroup test? We first of all have to show that the given subgroup, that means we are talking about ZG, that is not empty, right? So the second thing, we need to show that for two elements A and B belonging to the subgroup, their composition A star B, whatever it is, it belongs to Z of G. And the third property is that if we take some element from ZG, so its inverse should also be present in ZG, right? So here what is the identifying property of ZG? We know the definition of ZG. So the center of the group G, ZG, it contains all those elements from the group such that those elements commute with every other element of the group, right? So this is the definition. So first thing that we wanted to prove that identity is present in ZG. So identity, because it commutes with every element of the group G, right? You may write EX is equal to XE for all elements X belonging to G. In that case, identity would surely be there in this center of group, right? So therefore this is non-empty in nature. Now next property that we wanted to prove here is that if we take two elements A and B from the center of the group here, then their product is also there in the center of the group, right? So that means if we have A in the center of G, so according to the definition here, we would have AX is equal to XA for all the elements X belonging to G. And moreover, we have B in the center of the group G. So that means for this center here, BX is equal to XB for all the elements X belonging to G. So we have these two results with us. So here we wanted to prove AB also belongs to the center of the group. So that means AB should also commute with all the elements. So ABX should be equal to XAB for all the elements. So this is what we wanted to prove here. So let's consider the left hand side of this one. So we have AB of X. Now because of the associativity, because we are in the group, right, ZG, because all these members, they are present in group, so that means we have the property of associativity here. So we shift this bracket, right? So we may put this bracket onto BX. Now BX is equal to XB according to this property here, right? So that means it is equal to XB. Again, we can shift the brackets according to the property of associativity. Now AX is equal to XA according to the assumption that we made about the elements A and B. So it is equal to XA. Again, we may use the associativity property to disturb the brackets. So we put brackets over here, right? So if you see, we started with this property and we reached finally at this property. So that means AB of X, right, that is equal to X of AB. So it implies that AB commutes for all the AB commutes with all the elements X which are member of the group G. So that means the element AB belongs to the center of the group, right? So this is the closure property. Next, we wanted to prove that the inverse also exists in this center. For that, we assume that the element A is present in the center of the group, right? If A is present in the center, so that means according to the definition of the center of the group, AX is equal to XA for all the elements X belonging to G, right? And here we wanted to prove that the inverse also belongs to the center of the group. So that means A inverse X should be equal to XA inverse for all X belonging to G. So here for this, what we do, we pre-multiply and post-multiply this equation with A inverse. So that means we have this equation AX is equal to XA with A inverse pre-multiplied and A inverse post multiplied on both sides of this equation. So that we may use associativity here, we may put the brackets here, and the associativity here, put the brackets here, right? So we have this thing. Now A inverse A is equal to E, and A inverse is also equal to identity according to the properties of group, right? So this thing becomes identity here, and this thing also becomes identity here. Moreover, Ex is equal to X only, and Xe is also equal to X only. So this Ex becomes X and Xe becomes X here, so that we have Xa inverse is equal to A inverse X. And this is what we wanted to prove here in this part, right? So this thing implies that A inverse commutes with all those elements X such that X belongs to G, right? So it commutes, A inverse commutes with every element X of the group G. So that means A inverse now belongs to the center of the group whenever A belongs to the center of the group. And this is what we wanted to prove here. So according to two-step subgroup test, we have proved that the center of any group G is a subgroup of the group G. So I hope you understood this property and its proof. Well, that is it for this video. Thank you for watching.